Let's briefly discuss filters. In particular, let's talk about the characteristics of an ideal filter. And first we'll concentrate on a low-pass filter. And a low-pass filter has the following frequency response. It has a constant magnitude over a band of frequencies. The bandwidth is capital W here, and then it has a linear, will allow it to have a linear phase response. So the magnitude response of this ideal low-pass filter looks like this. This rect function has a width of 2 omega, so it goes from, 2W, so it goes from minus W to capital plus capital W, and then is equal to 1. So this is the magnitude response, and then the phase response is just this linear phase, which would give us a constant delay between the input and output here. And we've limited the magnitude here to between minus W and W. We would say that the bandwidth of the system, that's the width of the positive range of frequencies. So the bandwidth of a low-pass filter here is defined as being equal to capital W. It's not 2W, the entire width of this function. When you talk about the bandwidth, it's just the range of positive frequencies that are passed through the filter. We can see that there are a couple different cases in which you might use the low-pass filter. If all of the input signal spectral components are within the bandwidth of the filter, the purpose of the filter then is just to remove noise or distortion, interfering signals, and pass through our desired signal undistorted. If, though, on the other hand, there are components in our input signal that are at frequencies greater than capital W, then our low-pass filter is removing those, and we're getting a distorted version of the input at the output from our filter. In some cases, that may be desirable if we're trying to remove high-frequency components and do some that would result in a smoothing type of operation. So again, two main applications of low-pass filtering: passing through our signal undistorted and removing interfering signals and or noise that's present, and or possibly removing high-frequency components from our signal and smoothing our input signal, resulting in distortion, but in this case, desired distortion. So again, if the bandwidth of x of t is less than W, we know from our work with distortionless systems, then the output will just be a delayed version of the input. We also know that since h of t, the impulse response of our filter, is the inverse Fourier transform of our frequency response, we can take the inverse Fourier transform of our frequency response and get the following expression for h of t is equal to W over pi times the sinc of W t minus our delay. And it's a rough sketch of what this would look like. This is a sinc function, delayed so that it's centered at TD, so this would be the peak of our sinc function. that. Um, One thing to notice, and this would have a height of W over pi. So this is the impulse response of this ideal filter. One thing to notice is that even though these lobes get smaller and smaller in amplitude, the farther we get away from the peak of the sink, they do go on forever. So that means that the impulse response of this ideal low-pass filter is non-causal, and so we can't implement it exactly with physical circuitry, but we can approximate it by actually chopping off the portion of the response that's present for t less than 0. And so one way to come up with an approximation to the impulse response of the ideal filter and come up with a more practical filter that has some of the same characteristics is to multiply the impulse response of our ideal filter by u of t, resulting in a physical in a causal impulse response that then can be realized. Now, this may not be the best approach to coming up with the frequency response, the impulse response or the corresponding frequency response of a filter. You can look at other filter design techniques in subsequent courses.